Lesson 10 is on using conditional statements, and you've been using conditional statements. Pretty much every postulate, every theorem that we've talked about so far is based on conditional statements, but here we'll define them, and it's a statement of the form if P then Q, where P is a statement, it's a phrase basically, that's called the hypothesis, Q is called the conclusion. Now here's an example. If it is evening, then the sun is in the west. And like I said too, pretty much every single postulate, every theorem that we've studied has that conditional statement format to it. And we can see that here in postulates 7 through 9. Here's postulates 7 and 8. Both of those use that conditional statement phraseology where, like in postulate 7, the hypothesis is if two planes intersect, the conclusion is then their intersection is a line. Postulate 9 does not use that format, but those other two do, and most of the theorems and postulates do use the conditional statement format. Now, one reason we use conditional statements is that helps us understand whether something is true or false, and so we use something called the truth value, and the truth value that denotes whether or not a statement is true. And so look at that example there. If 3x plus 2 equals 8, then x equals 7. We've used a conditional statement there, but that's a false truth value to it, because if we did the math on that, 3x plus 2 equals 8, subtract 2 from both sides, we get 3x equals 6. 3 times what equals 6? Well, 3 times 2 equals 6. X equals 2. So that would be true if we had said if 3x plus 2 equals 8, then x equals 2. Now that would be a true conditional statement. So that was false because the conclusion was false. Now, something else we've also talked about is converse statements, and that's a statement formed by exchanging the hypothesis and the conclusion. And I've showed you that in some of the different theorems. They are converses of each other. Like theorem 6-5 and 6-6, those are converses of each other. So here's an example here of another one. If an animal is a fish, then it can swim. The converse of that, we exchange the hypothesis and the conclusion. So the conclusion becomes the hypothesis. If an animal can swim, the hypothesis becomes a conclusion. Then it is a fish. But that's not true. There's other animals that can swim. People can swim. So the converse is not always true, not necessarily true. Theorems 6-5 and 6-6, those are examples of when the converse is true. So we use conditional statements to help us understand if something is logical, if it's reasonable. Now, sometimes it helps to draw a diagram of a conditional statement, and these are called Euler diagrams, named after the scientist and mathematician Leonard Euler. Some people call him the master of all mathematicians. His name sounds like the word oil, but it's spelled E-U-L-E-R, and you pronounce it Euler. But he lived in the 1700s. Your textbook calls these Venn diagrams. So we can draw a diagram to represent that conditional statement. If an animal is a fish, then it can swim. And so what we can do here is have a group, and we'll call those fish. That's what those circles or ovals represent, as different groups of things. And then let's draw a bigger oval around that, and we'll just call that swimmers. So we have fish which are in the group of swimmers. So we can have seals. Seals swim, so we could put them in there, but they're separate from fish. And so that diagram helps us see that the converse would be false. If an animal can swim or is a swimmer, then it's not necessarily a fish. But if an animal is a fish, then it belongs to that group of animals called swimmers. It can swim. Well, let's go ahead and do some practice problems now. And in practice problem A, identify the hypothesis and conclusion in the following statements. So go ahead and write these statements out, and remember, if you want to, you can go ahead and pause the lesson right now and try to figure them out on your own. Then fast forward to the answer. If you got it right, just go on to the next problem. If you got it wrong, rewind and see what you did wrong. So on this first one, if 2x plus 1 equals 7, then x equals 3. Identifying the hypothesis, that would be this part here, and so I'm just going to put H for hypothesis, and then I'll put C for conclusion there. And then the next one, if the leaf is green, there's the hypothesis, then it contains chlorophyll. That's the conclusion. Then problem B, Determine the truth value of the following statement. If two angles form a linear pair, then they are complementary. So you just need to write true or false next to that. And actually that's theorem, or it's like theorem 6-3. Theorem 6-3 says if two angles form a linear pair, then they are supplementary, not complementary. So this is false. We can just put a capital F for false there. It would be true if that said supplementary instead of complementary. Problem C, find the converse of each statement, then determine if it's true. So the first one, we would say if x equals +2 or -2, then x squared equals 4. And that's true. So we can just say T for true there. And then the other statement, the converse would be if it is Sunday, then it is Easter. That would be false. Not every Sunday is Easter Sunday, just one time a year. And then problem D, draw an Euler diagram that represents that statement. If the truck is an F-250, then it is a Ford. Remember, the Saxon textbook calls those Venn diagrams, same thing. And let me draw it up here on the right because I'm kind of running out of room. I'm going to draw a big oval for trucks and then a smaller oval for Ford, because there's different kinds of trucks, Ford, Chevrolet, Toyota, and so on. We can draw another oval for F-250 trucks. That's certain type of truck. There'd be a set of trucks called F-250s. There's more than just one F-250. So those ovals, they represent the set of those trucks that are F-250s, and then within that is the set of trucks that are Fords. There's also F-150s, F-350s, and so on. And then within that, there's other kinds of trucks. But we don't need to show any other groups in this diagram. We just need to show and explain what that that conditional statement is describing. And so that's how we would do that with an Euler diagram. Now before we finish, let's talk about Leonard Euler for just a minute. And he lived from 1707 to 1783, and we've been describing his Euler diagrams or Venn diagrams. And just some interesting facts about him. He was considered the master of us all when it comes to mathematics, and he averaged 800 pages of original math research every year, and that's even after he went blind. The last 20 or so years of his life he was blind. He had scribes dictate for him. Now he was a Christian, and he was the son of a Calvinist pastor, and he preferred Bible reading with his many children and grandchildren to the rewards and honors that the court would give him. And he said in his book, Letters to a German Princess, "It is God, therefore, who places men every instant in circumstances the most favorable, and from which they may derive motives the most powerful to produce their conversion, so that men are always indebted to God for the means which promote their salvation." So that's one thing we do in geometry, is we're learning about different truths that have been around for thousands of years. Here's a truth, another truth that's been around for thousands of years, since the beginning of time, the beginning of creation. We can apply that to understand what Christianity means, what salvation means. How does it come about? Well, it comes about because of God. He provides the means which promote salvation of men. Okay, well that's all for lesson 10.